Welcome to run Numba functions in SQLite. What the F? Obligatory, important legal information. That's boring. Okay, so a little bit about me. Software engineer at Two Sigma. I've done a lot of open source Python tools, mostly in the PyData data analysis space. And I like interesting hacks. So I don't know if you'd call this talk interesting, but hopefully it will be. Okay. So just fair warning, like hacks ahead, many hacks. You probably should not use this software, but maybe you'll learn something and find something interesting. The main takeaway here is that Numba is probably more powerful than you think it is, and it's not that hard to extend, if you put in a lot of hours. So what do I mean by hard? Well, so the first thing we need to talk about is what it looks like to actually like stick something into SQLite. So what does it look like to extend it? Just a couple of terms we're going to be working with here. This is it for the sort of jargon is UDF, user-defined function, and a UDAF, which is a user-defined aggregate function. We're mostly going to be focusing on the second one, aggregate functions, because the sort of vanilla UDFs aren't that interesting. So what does it look like to actually do some of these things, like write a UDF or a UDAF inside of Python? You kind of just import SQLite 3, which is in the standard library. You fire up a connection. Here I'm making an in-memory connection. Define some Python function. Call connection.create function. Give it the name, the number of arguments, and the Python function object. And then you can start calling it inside of the database. So how many people knew this existed? Interesting. You can only work with, like, the inputs and the outputs can only be sort of like very simple types, right? You can't return like a list of dicts of strings to other lists of ints, right? You can't really do that. You can take strings, return strings, bytes, integers, floats, and that's about it. So UDAFs are a little bit more interesting. You define a class which implements these two methods, step and finalize. I'm going to go over exactly how that works and what it looks like. And you also have to define a constructor that takes no arguments, which initializes like variables that you're going to use during the aggregation. So what is the actual flow of like, how this class is used? So first, SQLite is going to initialize scratch space to hold intermediate values. And these are like the value, so going back here, this is the values of like total and count, right? So you actually need to instantiate the class. That's basically what's happening there. Then for each row in the column that you call your function on, it's going to call step with this scratch space and the arguments that you give it. Finally, after all rows have been traversed, it's going to call finalize, which gives you a chance to like tidy up and finish up your computation. So let's kind of be a little bit more concrete here. Let's say I have this table called T. It's got two columns, K and V, and I want to take the average of that with my UDF. So what does that look like? And to be clear, this is actually how SQLite itself does all of its internal aggregations. They're just defined using C, which we're going to get into later. So first we start with total and count set to 0. We then call step on the first row of V. Okay, so what that did was it added 1 to total and 1 to count. And then we go to the next row, we add 2 to our value of 1, which gives us 3, and we add 1 to the count. Nulls are sort of interesting. We basically just ignore them. Like we just don't update any of our values if we see a null. This is up to the user, of course. Like you can do whatever you want. I mean, you can drop your database if you hit a null or something. Don't do that, but you could. So nothing happens there. Then we add 4 to 3 gives us 7. We add 1 to the count, and then we add 5 to 7, which gives us 12. And we add 1 to the count again. So now we've traversed all rows. The next step is to call finalize, which, since we're computing an average, we divide total by count, and we get the average. What does that look like to use it? Well, it looks similar to create function or whatever it was called. You give it the name of the function, as you would call it in SQL, the number of arguments the step method takes, and the class. How many people knew this existed? I can't imagine the other, yeah, anyway. So this is what it would look like to use it. This with t thing is called a common table expression. I'm just doing something really boring and showing that you can actually call this function that is calling into this class. Give the average. So the C story is like a little bit different. There are a lot of similarities. There's a lot more boilerplate. You got to do a lot more. You got to be a lot more careful about allocation and things like that. So this is a little weird, right? This is what a step function, a user-defined step function would look like in SQLite. And I'm going to walk you through it, so it's actually not that scary, and you'll kind of see that there's exactly one piece of code we actually care about. So the scratch space has to be defined. Usually you define it at compile time. In this case, I'm making a struct whose like values are the same as my Python class. I just have to say what the type is. So the first thing I'm going to do is compute the size of this struct, like the compile time size. So it's going to be 16 bytes. There's going to be a double, which is 8 bytes, and an int64, which is 8 bytes. I'm then going to make this call into this. This is the SQLite C API, SQLite 3 aggregate context. And what that does is it says, allocate some memory, allocate exactly n bytes. And the interesting thing is that on the second call to step, it's going to give you the same memory you allocated on the first call, which allows you to keep updating that state. It gives you back a raw pointer, a void pointer, which basically has no utility at all except to be cast to something else. So here what we do is we cast that to our struct. This is a check to make sure that we actually were able to allocate memory. There's no else branch here, so there's no error handling in this version of the code. Because why handle errors when you don't have to? So the next step is we're going to get out the first argument, which is the argument to the function that the user provided. We're going to get the type out, which is sort of like an enum in C. If it's not null, basically if the value isn't null, pull out the value as a double and then do the thing that we actually want to do. Like this is the core logic to our aggregation. There's an interesting thing about SQLite is that it's dynamically typed similar to Python. So like in Python, in CPython, there's an object called PyObject, which every value in Python is an instance of. And similarly in SQLite, like if you have a string, if you have an integer, a floating point value, it's like SQLite value star. So it's very similar to PyObject. But this is the core thing that we want to extract. And we want to I want to make this simpler. I want it to run at C speed. And I also don't want to have to write all this junk. Finalize is similar. You still have to pull the aggregate context out, cast it, check for the null pointer, check to see if the number of non-null values is greater than 0, et cetera, et cetera. But you ultimately land on this singular piece of logic that you care about. So when I started working on this, I had basically no goals except to just make my head explode. But there's sort of a goal here, which is we want the Python standard library API, but we want C speeds. So this is a quick C refresher. Function pointers are pointers. Pointers are integers. Function pointers are therefore integers. Not all integers are function pointers, but some are. Maybe some people know where I'm going with this, but basically You really don't want to be dealing with like function pointers as integers generically, like generally speaking. They're sort of dangerous. So don't ever call a function pointer that somebody has handed you as an integer. Something like this is like really, like don't do this. Like don't make a form that accepts an integer and just like cast it to a function pointer, and you will be very sad. Okay. So who here has used Numba? Okay, cool. Has anybody extended Numba with like intrinsics? Okay, fine. Those people who raise their hands don't count. We'll get into that in a bit. So if you haven't used Numba, Numba is this very interesting project. Originally started at Anaconda when it was Continuum Analytics, and is now still being developed inside of Anaconda. What it allows you to do is write very fast numeric code in Python, and it uses a technology called LLVM, which will compile Python bytecode to machine code as Python is running. It's a very interesting piece of technology. It's extremely useful if you want to, like, if you have some computation that's difficult to express in a vectorized manner. Numba can really help you out. It also has some neat features like JIT classes, which are relatively new. They let you define classes that Numba will compile to machine code as Python is running. It's extensible. The dev team is extremely helpful. There's a mailing list on Google Groups, and they're, one of the things I went on there to ask for one of the things that I needed for this and how to sort of deal with the issue that I wanted to deal with, and so they're very helpful. There's also this thing called cfunc, which is basically the underlies all of the insanity we're about to get into. But first, let's talk about JIT classes. This is the average class from before, right? It's called, I didn't use total, it's value. But so that's basically all you have to do to like JITify your class. Like the first time I saw this, I was like this is insane. There's like what? Okay. So more or less, this is kind of like if you've done any C programming, this is kind of what that looks like. Numba will create two functions that take this struct average as the first argument, and then whatever other arguments you have in there, it will make function. Well, the function will take those as well. I'm like totally glossing over a lot of details here. There's a lot more stuff that goes on, but this like conceptually is like what it does. So let's get to a more specific goal. We want to call it JITted method from a C function that we define in Python that matches the SQLite C API. And this is like, what the heck is going on here? I mean, so what does cfunc do? Cfunc is sort of in the same lines as just like taking an integer and like casting it to a function pointer and hoping for the best. It's a Numba decorator. You slap it onto a function. You have to give it a signature. It's not going to magically like figure out. For people who've used Numba before, it's not going to magically figure out what the inputs are, and that's because it actually needs to like give you something back that can be immediately called in C, and C isn't very happy if you don't tell it what the types of the thing that you're computing on are. You can also do this, which is dangerous. But it turns out like this is critical for exposing Numba JIT classes and functions inside of SQLite. So I created something called slumba. Numba like gives you the LLVM code gen. User provides step and finalize methods. What the heck? What's left? similarly, important legal information, this important renaming information. Some of my coworkers suggested that I change the name from slumba to NUMSQL, which is pronounced numbskull. You might be asking yourself this question shortly. So numbskull kind of ties everything together. And I'm going to go through kind of defining like how you would use this stuff using numbskull. So you import another decorator. You give it a signature. You take your Numba JIT class, and then you write the same thing that you wrote before. So that's the first thing you do. Slumba then defines wrappers for step and finalize, which look strikingly similar to the C code. The main difference here is that like 80% of the code here is like sort of custom things that I had to write because they don't exist in Numba, and they're also like pretty dangerous, and they're also not anything that is like sort of generically useful, maybe with the exception of not null. So we're going to focus on step though, because that really has like the more interesting piece of code here. So let's kind of walk through what that's doing again, just like from the Python side of things. So again, like this is kind of unchanged. Like size of doesn't really exist in Numba. That was like probably the easiest thing to implement. But you give it, a context. It gives you back a raw pointer. Somehow that magically exists inside of Python. Then we cast that pointer to our JIT class type. If we successfully allocated memory, like call our method. So make arg tuple is like a total odyssey of weird like LLVM hacks, and we're just gonna like dive right into that. So what problem does make arg tuple solve? Like first of all, it's totally insane that you can like splat in a tuple into like something that's eventually going to be like called from C. So the thing we're solving is actually this sort of like type inference problem in kind of like we're basically saying, yeah, we're not going to solve that. So the problem is that this SQLite value doesn't have a type until runtime, right? So like in this case, what I'm doing is building an argument tuple, and I'm saying for each argument, give me the type. If it's a SQLite float, like append it to the tuple. If it's an integer, append that to the tuple. But I'm first like extracting those values as their C values, right? But remember when we actually like made people define this class, they have to give us the signature. So we don't actually need to do that type checking at runtime. We can just generate an argument tuple using LLVM right before you run this function with machine code. We require argument types. So it's not actually necessary to do that, and this is like most of what make our tuple looks like, except that there's like some totally insane magic in here, and I'm gonna show you like a sort of what that looks like. I fixed a bug earlier where it wasn't handling nulls, and like that made it significantly more complicated. So this is like, this was when I did this, it was like melting my face a little bit. So this is the core of what make our tuple looks like. And what it's doing is it's saying, okay, I have this argument type, which is what the user passed in. So in our case, it's a float 64. There's you're getting out a C-types function. You're then telling Numba to make that into some kind of Numba function that you can then call. You get an LLVM instruction out, FN. For the ith argument, you get out a pointer to that. You deref that pointer. and then you call our function on this element. I guess that would have been more useful. After that, insanity, Numba happily jits that this is like a impossible triangle with all these technologies somehow working together. Then you register your ag with the DB, and you can start calling it inside of SQLite. So what does slumba provide? Size of, unsafe cast, check if a pointer is not null, and this weird thing. So that's pretty much it. I have some other things, but we're running low on time. So if anyone, still have a few minutes? Okay. I don't know if I have anything super useful. Oh yeah, so I do have some vaporware and some really disappointing benchmarks, which basically like whole table aggregation is like much faster. I guess the good news is we're not any slower than the built-in SQLite functions. So this is I think saying average. If you take a whole table, I don't remember if this is indexed or not, but you take a whole table, you aggregate it, it's about 5 times faster to use Numba. It's like 1.5, for a high cardinality group by, like if the number, like the percentage of unique values in the column you're grouping on is high, you don't get that much benefit, and it's about 2x faster for a low cardinality group. I think like it's a 1% unique values in the low cardinality case and 90% in the high. There's like basically no reason to talk about scalar functions for performance. They're kind of neck and neck with Python. What Slumba doesn't do is anything that involves the heap.
What is scalar function?
So something that takes basically operates row-wise on a column. So like if you want to add 1 or something like that. Yeah, like incur.
I think that is. It's not much faster because the overhead potentially is going to be much smaller.
Yeah, I think the dynamic typing combined with like allocation and I/O is going to like dominate for like your actual computation. So Slumba doesn't handle anything having to do with the heap. Like if you want to do that, you basically have to take a void pointer in and like start calling into C types or some other totally insane thing that you probably shouldn't do. You probably would also have to extend Numba itself to make this work, like beyond making your own intrinsics. Lots of stuff looks like that, so this may or may not be a blocker for anything. I had a demo, which I can show very quickly. So let's make that a little bigger. Import our thing. Basically declare that, our class. So this is actually, SQLite recently added support for window functions. So I added support for that in Slumba. So we define our class, we connect to our database, we create our aggregate. Oh, that's the other thing. I have to use a special create aggregate function. Otherwise, you can't get access to the actual important object inside of SQLite because Python doesn't expose that in its C API, which is totally normal because it's a pointer. So, and then we'll just we'll call it. So it's comparing against the built-in average there. So that works. I don't know who asked that, but this works. I don't know if I'd say works for this library, but it does everything I've told you it does in this talk. And that's pretty much it. We have time for questions? Okay, cool. Well, maybe, yeah, if anyone has questions. That's,
So what got you to ask this question in the first place? Like, what was the winding road that got you to Numba functions in SQLite?
So I originally wanted to do this for Postgres, which it turns out is significantly more complicated, both from an actual just software point of view and the way in which user-defined functions are defined. They're also a lot more powerful. They have a lot more options about what kind of types you can take in and produce. But the sort of main limitation there, which I haven't thought too hard about, is that user-defined functions in C or compiled code are coming from a shared library that is on disk. Whereas all of this stuff is happening in memory. And SQLite takes a function pointer which lives in memory, and so that was like way easier. So I was like, let me get this into a database. And then I saw cfunc come along, and I was like, there it is. Cool.
Nice. Thank you.
Sure.